Second type of EMF. Well, as we talked about, all that we care is the integration of magnetic field line over certain area. Okay? So the first case is the area remains stationary. The second case now is we have a fixed magnetic field in space. But we can have the colloidal surface area now being a function of time. Right? So together, they also can have a time varying magnetic flux. In this particular case, you can induce the so-called motional EMF. This N stands for motional. You really have a device that is moving in space. Okay? So how do we analyze this case? If we have metallic bars or particles or colloids made of metal, here in space we have a constant magnetic field pointing into your eyes. And this metallic bar is moving with certain constant velocity u. For metal, we have lots and lots of free charges. Okay? So free charges moving in this magnetic field experiences force. And that force is basically the Lorentz force. Right? Lorentz force is the charge times the velocity, making a cross product to the magnetic field. So in this case, velocity is moving towards the right, and B is into your eyes. So U cross B pointing downwards for positive charges. If your charge is having a negative sign, then you have to multiply the negative sign. So the negative charges are going to experience the force pointing upwards. So eventually, as your metallic bar is moving in this space, positive charges will be deposited on the bottom, and the negative charges will be moved to the top. Okay. So now you have to think, when do the charge movements stop? Or do you think as you move across this space, more and more charges are going to be deposited over the two ends? When you have charges, right, positive charge and negative charge, what do they do? Well, they create electric fields, right? Electric fields are pointing from the positive charge towards the negative charge. So basically, you have another force, Fe, the electric force. So for this particle, the Lorentz force is telling it to move downwards, but as it moves, the electric force is telling it to move upwards. So at a certain point, when your Lorentz force is equal but in a negative direction to the electric force, the particle stops moving. Okay? That's called the balance action. But in the end, if this bar is indeed moving with a constant velocity, then we have positive charge and negative charge deposited over the two ends, and therefore we develop a potential difference, a voltage difference, and that voltage is called the motional EMF. Okay? So this is basically your Lorentz force making a line integration divided by the charge. That is your potential difference. Okay? have a closed loop, then the motional EMF, you have to integrate over the closed loop. That's it. Right? So let's just write it down. So in a case, even though the magnetic field is not changing as a function of time, but your circuitry is changing as a function of time or moving, then you can also induce the motional EMF. So let's take a look. This is a particular device. Okay, we will talk about its functionality later. You have a metallic wheel, okay, or a ring, a disc, that is moving with some angular velocity, right? And this disc, rotating disc, is positioned in a space with a constant magnetic field. So in this case, all the magnetic fields are pointing upwards. And this problem is asking you to calculate the potential difference between the outer side and the inner side, the origin and the outer perimeter. Do you know how to calculate it? Based on this equation. This is certainly the motional EMF, right? If this disc is not rotating, then V0 will be 0, right? So as you rotate, you have to ask yourself, well, everywhere on this disk, you can draw a line from the center to the outer perimeter. That's a radius, right? This radius can be viewed as a metallic bar rotating with certain angular velocity. So your velocity, in this case, is everywhere in the phi direction. So the phi direction cross B, so your force is pointing outwards in the radial direction for the positive charge. So you would expect to have positive charges deposited over the outer rim, and you have negative charges at the center. Okay? First thing first, before you jump in and you use mathematical derivations, please try to analyze the problem based on your physical understandings. So if you have positive charge outside, negative charge inside, what do you expect V0 to be? Is it going to be a positive number or negative number? Positive outside, negative charge inside. But now V0 is labeled. Point number 2 is connecting to the outer rim as a negative side. So basically you have to anticipate your answer to showing some negative sign, okay? Because positive charges are having higher potential. How do we proceed? Well, it's not difficult. We just use this equation, right? U cross B dot dl over the entire loop. But here the loop is from the center to the outer rim. Okay? U, as I mentioned, everywhere in the phi direction, r times omega. That is your velocity. Cross B here is in the z direction with a constant. So basically this force is in the radial direction and in the same direction as your differential length. Okay? You are trying to integrate over this length in the r direction from 4 to 3, or 3 to 4. Okay. All right, so basically that is what you have. Indeed, you have a negative sign. Okay? That conforms to our understanding. Okay? A negative sign. All right. So all the mathematical derivations are simple and straightforward, but what is the functionality of this device? I want 1 or 2 inputs. I'm not leaving this room until you give me some potential answers. What is the functionality for this device? We live in Taiwan, so we better know what it's good for. Because we don't like nuclear power, right? Taiwan, we have lots and lots of dams. What are dams for? 水库. Yes. Go ahead. Chinese or English, doesn't matter. 风力. Yeah. You can use wind power, okay, or water power. So wind and water, when you build a dam or you have this wind generating devices, those are used to rotate this disk, right? So when you have water flowing down, that is rotating your disk. Your disk is positioned in magnetic field, and then you have power. You have voltage. You have voltage, you connect to a resistor, you have current, right? You can store it. So this is basically probably the most valuable device that you learned in this class. We use power every day. In Taiwan, we don't like to have nuclear power, so we rely on hydropower, wind power, or maybe fire, right? We burn lots of garbage. But usually we burn garbage, the heat is used to rotate things, right? In the same way. So you have to thank Faraday for his observations. Okay, coming to the engineering part. If you go to Taipower, right, your first job, you go to the Taipower. On the very first day of your work, you were asked to increase this voltage. How would you do it? Your boss is looking at your resume. You got 95 in your electromagnetic course. Means you're very good. Right? How would you do it? If you want to increase or double, your first job is to double the EMF from your generator. How would you do it? Well, you look at this equation, right? You forgot everything, but you still have this PowerPoint slide. You look at it. Well, 2 is not going to change. Omega, tunable, right? B0, tunable. B, tunable. Which one would you choose to double your operational voltage? Meaning that you don't have to build a new dam, right? If you build a new dam, it takes about 10 years, costs lots. Some billions, but I mean, in the current case, how would you do it? This omega, if you want to change it, how would you change it? You probably need to build a new dam, right? Because of the height. The taller, probably the water drops, getting more accelerated, can rotate your disk faster. So you don't want to build a new dam. So the only 2 options are the B's. Capital B, non-capitalized B. So which one would you go? Which direction would you choose? Some inputs, please. You're finally back in classroom for answering my questions. Otherwise, why would you be here? Right? Don't be shy. Okay. People choosing this B, raise your hand. Yeah, one hand. You should raise your hand, right? Why? Well, B0, how do you provide this B0? Think about it. This question is asking you, or assuming that this disk is positioned in space with a constant magnetic field. But don't you have to ask where is the magnetic field coming from? If you're in a hydro power plant, don't expect to see this magnetic field coming from permanent magnets. It's impossible. Permanent magnets cannot provide a very high B value. Okay? So these are actually provided by electromagnets, meaning you input current to form this B. Right? So nothing's for free. So if you want to increase B0, you have to double your driving current. So you're not earning anything. So what is earning things for free? You just make your disk larger, right? If you make this B twice longer, then you make your voltage 4 times, right? And assuming you can make this area bigger without really increasing the weight, then basically you earn things, right? So remember, as an engineer, I bet you all know the answer, but you're just too shy. Okay? But we talked about this is building a new dam. This is sending in more driving current, but this is the free stuff. Okay? So in the future, if you understand the problem well, you know which perimeter is the most efficient and cost-effective perimeter to be tuned. Okay? All right. The last one, well, as you can guess, you might have the case where both the magnetic field and the coil circuitry area, they're both functions of time. So in that case, you have, well, the electric field and Lorentz force. Okay? Electric field produces electric force. So for this particular case, I don't want to go into the step-by-step proof. You are recommended to read the textbook on your own. But eventually, in this case, you have time-varying field, and you also have moving coil. You actually combine transformer EMF and motional EMF together, but luckily, the end result mathematical form is so simple. You're still creating a time-varying magnetic flux, and all you have to calculate is identical to how you calculate the transformer EMF. Okay? So even though in this case, you're still evaluating the time variation of your magnetic flux, and you multiply by the negative sign, right? So even though the mathematics are very difficult, the end result is very beautiful. Okay, let's take a look at one case. You have a rotating coil, right? So this coil, the area, is now a function of time because it is rotating. And your B, your applied B is in only one direction, but it is also time dependent. Okay? So this is another type of generator. This Faraday disk, oh by the way, this is called Faraday's disk. It is also capable of generating power. It's also a generator. And this is another form of a power generator. Okay? So the only difference is now you have a time varying magnetic field. Before we go on, what do you expect to see? The end functionality for this generator is quite similar to Faraday's disk, right? You have things rotating and you generate power. But think about it. The magnetic field changes as a function of time. This omega is your frequency, right? This is controllable. And this coil is rotating in space with respect to x-axis with certain angular velocity, omega. But this omega can be made different to this omega, right? So what do you think? What type of controllability do you gain? And you can actually control your output voltage or current frequency. Okay? So in the end, we're trying to evaluate the magnetic flux as a function of time, and we take its derivative and multiply by negative sign. So how do you express phi of t? Phi of t is nothing more than b of t times the area as a function of time. So basically, simple. Once you have phi of t, you take its negative sign. So in here, we have assumed the magnetic field is changing at the same rate as the coil, right? So you have this sine 2 omega divided by 2. You take the derivative of sine 2 omega, basically you have cosine 2 omega. So what does that tell you? Both your magnetic field is changing at the rate of omega, and your coil is changing at the rate of omega, rotating at the rate of omega, but in the end, the voltage that you create is having 2 omega. Okay? So your output voltage frequency is not equal to your inputs. And also, if this is omega 1, this is omega 2, that is your controllability, right? So such a simple device can give you power, it generates power, but now additionally to generating power, it provides you a way to control the output frequency. Okay? Again, you have to ask yourself, how to increase this V? Well, this frequency in here is really not helping, but this frequency is. Okay? So if you can rotate your coil, or you can change your magnetic field fast enough, faster, whenever the rotation or the rate of change to the field is faster, you increase your induced voltage. Okay? So every example, I'm not working on a lot of examples, as you can see. I don't like to deal with a lot of mathematical derivations, but what I like is looking at one example in depth, and you learn a lot. Okay? So there's no meaning for going over 10 examples, learning nothing, but we go over just 1 or 2 examples, but we learn in full details. And then you have to make cross comparisons, right? So what is the advantage of this generator as compared to the previous Faraday's disk? Way to change the frequency, and now you gain another approach to increase the induced voltage, right? Just by changing the frequency.